All right, so let's start. First, let me share the screen. Okay, so we're going to cover this few things. So let's start with the Mortensen. Okay, so in the first 4 labs, we have been using the DC power source and ammeter voltmeters. Now you're going to use something else. You're going to use the AC power source and the oscilloscope, which we usually call scope, in this lab. So you can throw away your DC power source and your ammeter voltmeters. We don't usually use those two when we do the AC measurement. Okay, so first, when you open the multisense, on the right-hand side, okay, you should see function generators. So this so-called XFG is something you will need to be using. Okay, this will be your AC power source. Okay, the other thing very important is our scope. Okay, it's over here. It's called oscilloscope. You don't need to use the 4-channel one, 2-channel is good enough. We don't have that many. Okay, so let's do a basic connections. So the part 1 of your Prelab is a very simple one, just asking you to connect between the function generator to the scope. So you can see there is a positive sign here, right? So positive to positive, okay? Negative to our ground, okay? And obviously you can add a ground or you don't, it just not really a big deal. Okay, so next things, you're going to set up the frequencies depending on what's the frequency you need. Say we have 1000 Hertz. So to set that up, again, you double click the function generator. So the frequency saying is 1000, saying the amplitude is 3 volt peak. Peak means when we say peak voltage, it means saying this is our okay, I'm just going to use this to draw it. Okay, saying this is our sine wave. Okay, peak voltage means the voltage between here to here. Okay, so this is V peak. Okay, this is V peak. This is peak voltage. If the question is telling you to find, saying V peak to peak, it means this to here. Okay, so this is V peak to peak. Okay, they are different. So you have to read the lab requirement very carefully. So usually, for example, anyone telling you he wants 10 volt peak to peak, then on the amplitude part, you will put 5 volt peak because you do not need 10 volt peak, right? So if it's 10, for example, it's 10 volt peak to peak, it means from the top to the bottom, they want 10 volt, okay? But for this case, we just need to have this 3 volt, okay? That's just examples. The last thing is called offset. Offset is we basically adding a DC offset to the signal, saying this is your original sine wave. You know, it start with the point 0 here, right? You can see it start with point 0. But if we have a DC offset saying, let me use a blue one, saying is offset by 1 volt. So it might look like this. Okay, which the offset will be, this will be your center line now. Okay, but this is where the 0 comes from. So this is the 0, 0 is still here. 0 is still here, so this is your DC offset. Basically, it's just everything shift up, right? Remember that you learned from high school that y is equal, right? A, right, sine x, right, plus b. Okay, whatever you have that b, you shift everything up, right? So this is that things. And in circuit analysis, AC source, we call DC offset. It's basically added DC voltage to the AC voltage source. So everything shifts up, right? Or you could have everything shift down. So saying we give 1 volt, okay, offset going up. So you can already see it. It will be what? This will be a 3 volt peak signal, right? 3 volt, okay. The high from here to the center line will be 3 volt, right? Okay, and where's the 0 point? The 0 point will be somewhere here. Sorry, somewhere here actually. It will be 1 volt above, so everything shift up. Let me just use a different color so I can show it. So this will be your 0, and this will be your 1. Okay, so everything shift up. You will see it. Maybe I didn't explain well, but you will see it when you do this. Actually, when we run it, it will be more clear. So as you can see it now, okay. So when you run these things, you will see the things is too small, you can't see it when we press the running. So when you press run, it's just keep running like that. Okay, so the good thing is, the good way to do it is you should always try to either pause it or stop it, because if you keep running, you can't really see it. After you stop it, you will see the wave on the scope. If you don't like the black background, which is sometimes is the color is too dark, you can't see it clearly, you can use reverse. Or if your computer have a good display or something like that, then you can see it, then use that. It's fine. You can reverse it and see it clearly, or you want to print on the papers. Okay, but the next thing is very important is the scale on the bottom. Okay, you have the time-based scale, channel A scale, channel B scale. We are only using channel A, as you can see, so nothing to do with channel B here. When you adjust this one, say I go lower, you can see the wave get expanded, right? If I go higher, oh, someone have a questions? Sorry, what's the difference between a common negative function? Not really different. Some people using the negative part, and then they still connect to the COM. The COM is just, we usually call that common ground. Just you need to remember on the AC case, there's only one ground. When you're actually connecting it, the only ground is on the function generator's ground. Okay, so anyway, let's adjust the time scale. So when you adjust the time scale, you can see it is get expanded, right? So you can see it more. Okay, another questions? Oh, no problem. Okay, yeah. And we can adjust the channels so you can see it more clearly now. Now, because I add this 1 volt DC offset, so everything shift up by 1. Originally, the bottom peak should be minus 3 volt to positive 3 volt. Now it's only go from the negative 2 volt. If I move the cursors, you can see the cursor is on the left. This part is important because you're going to use that for your pre-lab, okay? So the cursor is actually on the left. You will have 2 cursors. There are reasons they give 2 cursors. So if I move this cursors to the bottom, you can see the number it's give you is minus 2979, right? If you want to be accurate, okay, what you can do is right click on the cursors and you go to Y mean, which is give you minus 2.995. You notice we giving amplitude of 3 volt and DC offset of 1 volt, right? So the result is giving you very close to what you expect. Yes, any questions? So it doesn't matter. Use the comment. Yeah, it doesn't really matter on that case. Just yeah, it's just the ground. You can use if I redo it again. Okay, that's a good question. If I do it again, I know some people using the negative part. If I do it again, you will see a very similar result, right? Okay. Let me just reduce it again. You can see a very similar result, right? Everything shift, right? Okay, if I connect to this one, it's the same, right? It's just the scale I'm using is a little bit different, but everything still shifts to that point, right? Can you guys see it? You can see it, right? Okay, so you see here, minus 1.9, the top one should be somewhere to the 4 point, yeah, that's it. So it's no, I usually recommend to use the comma because the comma means the common ground, but if you're using negative, there is no difference. Your TA would understand it totally. Okay, so anyway, let's go to the next things is we need to know where is the okay, sorry, let me just adjust a little bit so you can see it better. Okay, so now let's move this to the Y mean. Okay, so Y mean, as you can see here, because we are using the cursor 2, you can see there's a tiny 2 here, right? The cursor to the value give you is minus 1.995. Okay, originally what I'm saying that T2 minus T1 is where the T1 is to T2. From here to here is always 3 volt, right? Because the peak voltage is that. Okay, then the other one we can go is if you grab it and then you say go to the next max. So now one of the question on the Prelab is asking you to find something like this. Okay, so for the sine wave like this one, the maximum voltage you can have is 3.995 volts. The minimum voltage you can have is minus 1.995. All right, it's a little bit different than what you expect to have, right? You would expect to have 4 and minus 2, but in multisim, when they do the simulation, it's a tiny bit off, okay? So they add a lot factor in there, so you don't have to worry. Just write down whatever you get compared to the theory values. Theory value, you should get 4 and minus 2, right? But this is what multisim have. And you will see more different result when we actually do it in person lab. That's all you need to record it. The next thing is it might asking you to find the period, right? To find the period. To find the period, what is period referring to when you doing a sine wave? So sine wave is like this, right? Okay. Sorry, do I have to draw again? Let me do it quickly. So save this. The sine wave. So saying like this, the period is from here to where it's count. So when it's crossing the 0 point, saying like this, going up, okay? From here to here, this is we call a full period or 360 degree phase, right? Okay, so the time between here to here is where we find that period. When we have DC offset, okay, to find the full period, the best way you can do it, one way is using the peak to peak. So if I go to another Y max, so between here to here, okay. If there is no offset, you can use the zero crossing, which we usually recommend you to use zero crossing anyway. Okay, so now how do I know the period? The period is from T2 minus T1. And the Multison already did that for you. So you can see here on the bottom, can you guys see it here? So where at my mouse pointing, T2 minus T1 is equal 1.00 milliseconds, right? So 1.00 ms is equal what? Is equal 1 times 10 to the minus 3 second, right? And which we know that F equal what? 1 over T, right? And then you can go 1 over 1.0 ms, then you can find your frequency. Okay, what is our frequency? Is 100 hertz. If you do the 1000 hertz, I mean. So if you do the calculation correctly, you will get 1000 hertz. It's just very simple stuff. Okay, so this is one thing we're going to do it. So anyone have questions on this part until this part? Okay, so I think it's pretty simple, right? Just connecting the function generator with the oscilloscope, and then you just do the measurement on it. And you can always print the screen, just press print screen. I like to use pen to do it. So when I do print screen, okay, then I open it up and I just paste it there, and then you can do the analysis afterward. It's totally up to you. Okay, so now let's do the next things. We'll have multiple resistors, so I'm not going to use the same value as we have on the lab, but we were using a different one. Okay, so saying we have one here, another one here. Okay, so now I'm going to use 2 channel. Okay, so this is my circuit. Now I'm going to connect into a second channel between the resistors, which this one still goes to the ground. Okay. So now I have, basically it's like a voltage divider. Basically the circuit is look like this. Okay, I'm going to just quickly draw it. So it's like one resistor here, one resistor here. Sorry, I draw really bad. Okay, so this is your AC input. Okay, so this is your VS, right? So this is 1K, this is another 1K. The question asks you to check. So this is channel 1, this is channel 2. Okay, so something like that. All right. So this is what's happened to the circuit when you build it. Okay, so we just need to run it. Then you will see, hey, where is my channel 2? They are both up here. Oh, wait. Okay. My check. Oh, wait a second. Just fix this color. Okay. Oh. Okay. Here, where you connecting it? This is very important. Okay. Okay, so originally I was connecting wrong. Now guys, okay, let's see if we skip step, it's not going to be good. Okay, so let me do it correctly because I connected the result to the ground. Okay, so we have two resistors like this, right? Okay, from the input goes to here, okay, and come back to the common ground. Okay, you can connect this to the ground, or some people using a negative, it doesn't really make difference. Okay, here, and this one is between the resistors, so channel 2 here. Okay, to the ground, to the ground. All right, now let's run. Okay, you will see 2 waves like this. Okay, so stop it. You will see 2 waves. Well, from your knowledge, obviously you can tell the higher one is this point, right? because this is your original input sine wave, and this is where your output sine wave, or we can say the voltage dividers sine wave. So the voltage is a little bit lower, as you can see, because it's only 1K to the ground. Okay, sometimes it might be difficult for you to see which one is which. All right, saying if I change this value to saying 10 ohms, okay, if I change this to 10 ohm, okay, then when I have then saying if you're using the exact same deviations, saying 2 volt and 2 volt, you can't really tell which one is which, right? It's really hard to see it if they have the same scale. So sometimes you have to move this, or the other way, usually I do it is you click where you connect the channel 2 or channel 1. You click the wire and you right click it and then go to the segment color. Okay, click the different colors, saying green one. Okay, now you rerun again. You will now see it. The channel 2 is showing in green. Okay, it might be easier for you to see it, but it's up to you how you want to handle this. There is no right or wrong on this thing, or which color you have to use it, as long as you can visually see it. All right. So far until this part should be fine, right? I'm assuming that. Okay. All right, now let's go to the next part, is where we have the RC circuit, where you're going to measure the phase difference. Okay, so to measure the phase, we need either capacitors or inductors. So to find that, when you are on the multisense, click these things on the top, or master database. Okay, and click the group, go to basic. On the basic part, you will see capacitors. Okay, so I'm going to use 1 UF. All right, I'm going to connect like this. Okay, like this. All right. And then again, I'm going to change the color. I'm going to change the color to green. And my frequency, I'm going to lower it down to 300 hertz and no DC offset. Okay, because DC offset will make this thing a little bit messy for you to see it. So now let's click this up. Okay, so remember at 300 hertz, we're using 3 volt peak, and okay, you know what? Let me reduce to 100 hertz actually. Okay, so all right, let's do it. Okay. So this is what's happened. Obviously, sometimes it's too close to see difference. So let's change the value. Okay. All right, sorry guys. This is better. Yeah. Okay. Sorry guys. Okay. Okay. Don't worry, when you're actually building it, it's very, very simple. Just because I'm kind of rushed to do it. Okay. Let's choose the green color. The input is that one. Okay. We choose. I choose 500 hertz. 3 volt peak. Let's start it. Okay. Let me pause it. All right. Decrease the things. Okay. Very clear to see it. I can't choose exactly the same example as we have on the lab. Okay, but what I'm trying to tell you is if it's both resistor, you will see the intersect at the same point. But because this is there's a capacitors here, you can see it. There is a, how to say it, there is a phase difference. It might be more clear when we do using a square wave. So how to see it, this. Let me change this to like this. Okay. This is what you will see for lab 6. Okay. Okay. So now I change my input to a square wave. The output will be like the green one, which the output is where it just right in front of the capacitors. So the red, okay, let me turn this off so you can see only the red now. Okay. The red is your input. Okay. The green is your output. You can see they look a little bit different, right? There is a time delayed. So just think about this way. When you have a battery, when you try to charge even your cell phone, right? When you plug into the AC port or the power socket, it won't charge immediately. There is a time delay. So that delay is where our phase come from, right? So that's why when you're using the sine wave, it will be more clear to see it. So the sine wave is here is that this between this one here. I'm not sure if you guys are able to see it clearly. I change the time scale. So you can see this right over here and here. The difference between them is our phase difference. Okay. So using the lab example. Okay. Okay. Actually, let me use one. Let's use this example. 100 hertz. Okay. Okay, so now, okay, that's I use a different values. This should be more clear to see it now. Okay, so to measure the phase difference, first you find the 0 point. For example, the 0 for the green one. Can you guys see it? I'm at the 0 for the capacitor one, the output voltage. So make sure it goes to the 0 crossing, where the green wave crossing the 0. So leave this cursor here. Now move another cursors to the closest one. Always on the left-hand side when they both rising, okay? You don't want to compare one rising with the falling, okay? So you do not want to put this thing here. That's wrong. When it's rising, you compare with the rising, the nearest rising on the left-hand side of that wave, okay? The closest one. You will able to see it easily. The value we give in the lab is very clear, okay? So now just put here, okay, I'm going to record down these values, which, you know what, let me just take a print screen. So it's more easier for you guys to understand it. Okay, so this is my first part, okay. All right. Okay, so I have this 2 point, as you can see it, I have this 2.439 millisecond. It's between here to here. That's 2.439 milliseconds. Okay, the next things I'm going to do is I'm going to move this all the way So remember, we need one period, right? So move this all the way to here. When the red wave, the input wave is rising, it should be 10 milliseconds, but because we have 100 hertz, right? It should be 10 milliseconds, but there will be a tiny difference when you move the cursor, same as when you do that in person. So 9.981, okay, 9.981. Let me take another print screen. All right, so 9.981. Okay, so between here to here. All right, so now let's do another one. So it's 9.981. So you can see it is this value here is 9.981 millisecond. Okay, so this is delta x. Sorry, delta t. If you call it delta t, this is t. This is period. Okay, so what's the okay? So what's the phase? Very simple. The phase, okay. The phase is equal. Okay, the phase is equal delta t over t, which is times 360 degree. Okay, so that is straightforward. 2.494, 2.439, 2.439 divided by 9.91 times 360 degree. That's equal to, let me do the calculation, 2.439 divided by 9.981, okay, times 360, that is 87 degree, 87 degree. Okay, so we got 87 degrees. All right, and that's basically it. So when they ask you to find it, yes, you can use the green one. Exactly. If we okay, let's see. If we use the green one, does it make any difference? No. They both have the same frequency. Now let's try to use the green one. 9.962. Well, it's not exactly the same, tiny different. See, the other one we got 9.981. This one we got 9.962. It's just where your cursor, where I can move a little bit further. So the value is, or if you want to be accurate, remember what I use it. Okay, you can use this set value to 0. So when you find 0.0 crossing, but you know, the tiny difference is totally acceptable. They have the same frequency. So the only thing difference is they have different phase. So for this one, the wave between them will be 100 hertz. The frequency for both component will stay in 100 hertz. Okay, the frequency is the same all the way. You won't see different frequency until you go to third year. Okay, yeah, all right, cool. Our calculation for the lab should be in degree now. Yeah, it should be in degree. We use degree. Good questions. So in degree or radians, the lab 5 is being designed using degree. So as lab 6 and 7, all very simple. So the good news to let you guys know it. Okay, unlike lab 3 and 4, which all the TA understand that it's your first time to build the breadboard, and it's kind of complicated. But from now on, building the breadboard is not that complicated. You won't have more than 3 components on the breadboard at this time. But the very important thing is understanding how to use the scope. So this is the hard part. You will using the oscilloscope very frequently for the next 3 years for your university life. So be familiar with this. It's very, very important. So again, how to measure the phase? Let's go from the beginning again. Okay, so grab this to where it's rising, or if you want to do the following, it's the same. Okay, but if you do the following, it have to be both following. So saying following to following. So this is a green one following. This is red one following. So following to following, the difference is 2.079. Okay, check the one we have. what we have 2 point, a little bit difference. Then you do another one when you do folding to folding. So grab this one to here, then you will have something similar numbers. But it's very important. If you go folding, then you go folding. If you go rising, then you go rising. And then the rising have to be the one right immediately behind it. You cannot say, oh, I use this rising and I compare with this rising. Obviously, it's not right because there's so many different zero crossing point between it, right? So you want immediate zero crossing point. So this is your delta T. This is your period. Okay. Okay, I guess I confused more people. Okay. Yeah, the post reported. Don't worry. No, it's T2 minus T1. Very good, very good. So you're looking at the T2 minus T1 value here. Exactly. It's telling you the T1. So this is telling you the time for T1 is sitting at 80.024 milliseconds. This is telling you the T2 is sitting at this. You can use calculator to do it, but Mothersson did for you. You don't have to worry about it. T2 minus T1 already telling you. So, but if you somehow swap them, no worry, it just give you a negative number. If you get a negative number, you know the time won't be negative. So just just simply use that one. Okay, and then on the on our report on our lab manuals, the formula is already being provided to you. So in the pre-lab, you just use this equation, theta equal tangent minus 2 pi f CR, then you're able to see the phase difference. Record that down, and when you do the simulations, do the same thing. It's asking you to find period, delta T measured in motorsense, and theta, which you do the same thing as what I did. You just have to keep changing the frequencies, saying 3000. So when you increase that to 3000, you see the phase. You see, this is kind of hard to see it, right? So you're just going to, what I usually do is just adjust a little bit, adjust the scale. So this 3 scale button is very important. When you adjust a little bit, you can see the wave more clearly. And don't use the wave at the beginning. As you can see, at the beginning is messed up. See, at the beginning is messed up, which this Mothersson try to simulate in real life when you input it, the responding time. There is the things you will understand better later on, which you don't have to worry too much about this. Okay, now when we increase the frequencies, now everything will be changed. So this time I have 83.176. Okay, so when I increase, so this is when I add what was that, 100 hertz. Okay, so when I increase the frequency to what is it, 3000 hertz. Okay, so when I increase the frequency to 3000 hertz, what I'm going to have is, when I increase the frequency, now my delta T is equal 83.176 µs. Okay, at 3000 hertz. Okay, and my period, obviously you don't need to use this. You can still find the period, but let's be more precise. Okay, so it's 328. So we got 328 for the period. All right. Okay. So the T is equal 328.922 µs. Okay, so our phase is equal what? Is equal 83.176, 83.176 divided by 328.922 times 360. Sorry, 360 is equal 83.176 divided by 328.922 times 360. Okay, we have 91 degrees. Okay, so something like that, you see the phase increase. Okay, so I'll increase to 91 degrees. If you go lower frequency, you will see a different result. Okay, so this also, just let you know, you don't really have to know it now. This is also act as a filter. Usually if you change the position of the RCs, either high pass or low pass filters, you can see it when the frequency stay at a certain point is either high pass or low pass, because any frequency higher than that or lower than that won't be going through it. That will be later on. Okay, so now let's go to the in-person part. Okay, just want to make sure you guys know it. Okay, so if you've been assigned in ENG301, you will be using this kind of scope. If you've been assigned in ENG302, you've been using this scope. They are the same, very similar. Okay, so now let's see how to build it when you actually get to the lab. Okay, just want to go through it. Now, if you have any pre-lab parts, let me know it. Pre-lab issues, let me know. Okay, I'm going to stop sharing. Okay, I'm going to use my camera. All right, guys. Okay, so here we go. So these are the two things we're going to use. Let me just take myself. Okay. So everyone can see it, right? I have my. So when you get into the lab, you will see function generator and the scope and your breadboard. All right. So the binding post you did for lab 3 and 4 still very important. Now we only need to use a 2-port. The first thing when you get into the lab, okay, from the function generators, you will see a banana cable on the other hand. Okay, the red one and the black one. Just remember what I say. The black one is your ground. All right. So on the breadboard, okay, plug the red one to the red part. Okay, plug the black one to where your ground's being assigned. Okay, like that. Now your rail is being charged with the AC voltage input and the ground. That's it, like that. Okay. Next things, resistor, capacitors. Okay, capacitor look like this in your how to say, in your lab kit. Okay, and you probably already see something like this, which don't touch this. This is your inductor. We will be using for lab 6. So not now. Okay, just keep that in good conditions. You will see that. We have a lot different capacitors. So each capacitor have a code on there. If you can take a look, okay. The example I used, I believe I was using 1 μF, right? Using 1 μF, okay. So let me just share my screen one more time. Okay, so I believe I'm using 1 μF. Okay, so 1 μF, what is the code for that one? I believe is here. So I'm using, so the one that we are using for lab 5 is 0.1 μF. In your lab, we are using 0.1. Let me just make sure. Yeah, we are using 0.1 μF in your lab. So when you come to the lab, you will need to grab 104. Okay, see on the capacitors, the green one, there should be a code 104 on there. Okay, that's a capacitor you need to find. And but for this example, I'm using 1 μF. So my code should be what? Should be 105. See, just 10 times 5 to that nano F. That's how the things calculate. But anyway, let's go back to stop sharing. Okay, so simply plug them in series. Okay, so like this. Then can everyone see it? I'm pretty sure this is very simple, not a big deal. The good thing about the capacitor we are using in this course is non-polarized. Okay, so that means when you see it, both leg are the same equal length. Okay, so it doesn't matter the polarity. If there is a polarized capacitors,
which usually the capacitance will be larger. You will see that in third year or second years. So be aware about the polarity for those kind of capacitors. But for this one, it's totally fine. So now we just finish connecting. Now, I'm plugging this. Okay, before we do anything, we always need to check the input wave. Okay, so this is your function generator's wire. The other one is your oscilloscope wires. Okay, so you will have three BNC cable on your table. Okay, sometimes it's really hard to see it, so it's important you manage your wire properly. Just remember lab how we did for lab 4s when you had dual power supply, a lot of cables on there. Okay, so now let's go back to here. Okay, so let me explain the function generators. When you started, the first key you should press is this waveform. You're going to choose different waveform type. In this course, you're only using two different waveforms. Either, okay, let me put this thing again closer. Either we're using the sine wave or the square wave. So you don't have to worry too much. Later on for third year, you may using triangle wave, okay, but not at this point. So the only two waves you need to worry is sine wave and square wave. For this lab, it's even easier. We're only using sine wave. So just press sine wave. Next is giving you three different options for you to input: frequency, amplitude, and offset. So saying frequency, let's say 300 hertz. Okay, the amplitude, I'm using 3-volt peak. So press that. Okay, add that input. Okay, now connect your function generator to your scope. Okay, very simple. Red to red, black to black. Okay. You may wonder, there is nothing showing up. Just remember in your lab, lab for everything, right? You won't turn on until you press the on button. So they have a safety feature here too. So the only way to turn on your AC power is press this. Okay, now your things is on. You can see it. And when I turn on, it's showing up on your scope. Now we have the wave showing on the scope now. Okay. So few buttons you need to understand it. This things is the most expensive equipment for in the rooms. Okay, the most expensive equipment in the rooms, and the school spend a lot of money to purchase the brand new scope for you guys, for also for us, for everyone, is to want to give us the best learning environment. And this is very important for you because scope is not only using this course, it's basically every single course afterward. Anything you touch with signal, everything's even control, you will see this a lot. So you need to get familiar with it. And the important thing about lab 5, 6, 7 is all about how to use these things. Okay, so this is the important part. The few key I need to explain to you guys is the first keys you need to know is this white key on the top left. It's called auto scale. Okay, auto scale. So press that, it will able to clean the wave. Okay. Now you see the channel 2, the green wave is pretty messy because obviously we don't have a channel 2 input. I only connect this to channel 1, right? I only connect that to channel 1. Nothing to do with channel 2. What you can do is you can turn off channel 2. Okay, so just let channel 2 go away. Now you have this wave sitting on the top. Remember, it's a little bit different than what you have on multisense because multisense start with the middles. This is how the scope always does, is split the two wave. So the first thing you need to do it is on this vertical knob, you see that there's a verticals, right? Vertical here. Okay, this vertical knob, the bottom knob, push in there. Okay, push it. You see the wave will centralize it. So now the wave is in the center. Okay, when I change, so this is called position knob. So this is called vertical position knob. When you go up and down, you can move it up and down, but it's not going to change anything. The wave is still there. It just is change how it displayed on the scope. It's not going to change the wave itself. Okay, the only way you can change the wave itself is to change the function generators. So if you wanted to go up and down, in real case, you're using DC offset. But this is not really providing a DC offset, just change the position. I hope this everyone understand it, right? Okay. Because I see some students get confused for this even when they got to the third year. Okay. Now you can use this to adjust the scale to make it larger or smaller, but it's not, again, it's not changing the wave. Scope is more like your DMM, right? It's like your multimeters when you do the lab 3 and 4. It's just what you see it. It's not you changing the power supply. You did not change your power supply. Your only power supply is your function generators. You see, when I change this, when I change the scale up and down, you can see this number on top is changing. This is called block unit. So each block is 1.48 volts. So when I increase it, obviously each block number will decrease, right? If I decrease it, this number increase. That means every single block is now 3 volts, right? Because I'm inputting 3 volt voltage. Now, so you are good with this. Okay, now we're going to see the horizontal knob. Horizontal knob, when you turn it, you see you can expand it. Okay, when you shrink it, you can shrink it. Okay, same thing as we did on the multi-set. Remember the scale part, the 3 different scale knob is very important. So you can see now it's 3.3 milliseconds per block. So that means each block is 3.3 milliseconds. Sorry. Okay, and then the horizontal position knob, which sometimes we need to use it to make sure the zero crossings at the center. It's depending on what kind math performance you need to math calculation you need to use it, then you do that. It's not something very important or very useful for at this point. Okay. So far all this you are good with it. Okay. The next thing is very important is the cursors. Okay. For your lab, basically entire lab, you will using the cursors a lot. The cursor key is here, right here. On the beside the measures, cursor key is here. Press that cursors, okay. You will able to use 2 cursors or even 4, depending on which mode you use. I usually prefer to use track waveform mode. So the cursor will stay on the wave. So track waveform, okay. Let me just put this to a wider range so you can see it better. Okay, so now I'm going to use the cursor 1. Okay, so I'm going to move my cursor 1. When I move it, can you see the cursor is moving? See, this thing is moving, is tracking the wave, right? So if I want to know the peak voltage, you keep scrolling, for example, at this point, okay, I think this is the peak. Okay, then you press this, run and stop. 3.05645 volt. Okay, so that's your result. You can use a cell phone to take a picture of this, or you can plug the USB here and press save to USB. I already set every scope to save the file as a PNG file in a lab. But you know, because I know nowadays not everyone have a USB storage drive with them, so using a cell phone is totally fine. Just make sure you take the picture clearly. You can see it. The important thing is you must able to see the white value, otherwise it's meaningless. Okay, now let's stop it again. So let's get another cursors. Let's get the cursor 2 because we need to find the difference, right? So now let's see. Now cursor 2 is coming out from the other side. You see it? So now let's move it to the bottom. Okay, and you can see, hey, it's giving me minus 3.06. So that's your minus, so that's your V min, that's your V max. All right, and it's also give you delta X, which delta X is what? It's your delta T. It's your delta T in the pre-lab. Sorry, delta T you need to find for the phase. Okay, so this is the basic one. So we done this part. Okay, now let's go back to here. Okay, I'm going to disconnect it and actually connect to the circuit. Let's do it this quick. I don't want to take you too much time. Okay, so again, turn this off just like when we do it in lab 3 and 4. Whenever you turn on the power, so whenever you want to change the circuit, you need to turn off the power. So treat this as your power supply. Function generator now is your power supply. It's actually providing the same thing, same power like you did in the DC. So now I connect everything like this. Very simple circuit. You won't have circuit that more complex than this. See, a resistor, capacitor, ground. That's it. Now, this is important part. This is important part. Okay, so please just take a look. Okay, so when I grab my channel 1 cable from my oscilloscope, you will have a red and black one like this. Okay, the black one is where it connects to the ground. Okay, where is your ground? Your ground is this part. The ground is the black one on your breadboard. This part. Okay, so just it's like an alligator. Just grab it and plug in there. If you get the banana one, just use the alligator to connect there. Okay, so the input is where the input is here. So just grab it here. Now you will have an input wave. So when I turn this on, you can see it. Hey, the same thing appear on there. So it's totally fine. Now, your output, so channel 2's cable is here. Okay, this part at the end of the red wires, I want you to grab a short wire like this. Okay, like something like this. Okay, and if you see it on the, let me just, oh, someone was asking a question. Okay, yes. Would it still use negative values or take it absolute? Would we still use, sorry, what? Oh, I mean, for this one, we just need to know the phase difference. So use absolute value will be better. And I told all the TA the phase is actually positive phase, so don't worry about it. They all know it, don't worry. Yeah, that part should be fine. Let me just share the screen again. So sorry, guys. Okay, so let me just go back to where is my circuit. Okay, so you can see a channel 2 is connecting before the, so channel 1 is where you have for the original function. Channel 2 is where the before the capacitors, right? Just where the resistor connect with the capacitors. Okay. Now let's see this. Okay, let me stop sharing again. Okay, so see here. So this is where your channel 2 is. Resistors and capacitors. So grab this red one and plug on the same row. Okay. Until this point, you guys should have no problem on connecting it, right? Okay. I know some people may still have it. Don't worry, you will get familiar with it. Okay. And then the hard part is this thing. Okay, the black one joining up with this huge things look like ICU things. Okay, so sorry for that. I mean, but you will see this pile up even higher. When you will see like in 3rd and 4th year when you do the breadboard, the ground will be really huge because you have multiple channels. Okay, now everything connect. Okay, turn on the power supply. Turn on channel 2. Hey, you can see it. Okay, let me move this thing away. Okay. This thing away. Okay, again, first thing we press is over scale. You can see it, the 2 wave is there. First thing you do it, press to the center, make them both in the center. You can see there's a phase difference, right? You can see there's a phase difference, and you can see it's noisy. It's noisy because whenever you have capacitance or you have inductance, is not that, how to say it, it's not that high resolution. So one trick I always tell everyone is you can add a filter there. So what we can do it is on here, you can see there's acquisition button, press that, and then go to acquisition mode from normal to high resolutions. you can see the wave is much more clean now, right? Okay, use the horizontal and the vertical knob to make it more clear for you to see it. Okay, all right. Okay, I think this is good enough. Now use the cursors to measure the phase. Okay, again, we do the same thing. So this one, let's put to here. Okay, you guys can see it. I hope you guys can see it, right? So I put this here. Now using cursor 1, go to channel 1. Okay. So hey, here we go. What I got is 800 µs. Can you guys see it? So it's 800 µs for this. This, you see the rising to the rising, right? So I'm going to just write down 800 µs. Where's my pen? Okay, 800 µs. Okay, so that's delta t. Okay, now I need to know the full period. Okay, use the same thing. Now move this. Actually, move this one to cursor 2 and change the source to 1. Okay, so I'm going to move this to where the rising is. Right, the rising 0 cross. You can see it. The total period is 3.340 ms. Okay, 1 ms is 1000 US. So we will have 800 divided by 3340 times 360. We have 86.22 degrees. Oh, very similar to what we get, right, on the multisense. So the idea, everything is very simple. You just need to know how to use it. Okay. That's basically it. All right. Any questions?
Hi, when will the recording be posted?
Yes.
Yeah.
So, sorry, I didn't hear it. Sorry.
Yeah, I'm asking like when will the recording be posted?
I will post recording immediately. Yeah. Just give me 1 second. But any questions? I won't answer questions. Can you do how to get phase difference again? Which part, multisense or the actual? Because in person we will still cover it. Okay. You know what? Let me do it the one for the multisense. Okay. Just give me 1 second. Stop video, right? Stop video, and I'm going to do the screen share. Okay, let's go this things. Okay, so until now, you guys probably know it. The important thing is the scope. Really the scope. Okay. So, did I share the screen? Did I share? I'm sure. Right. Okay, I'm sure. Okay. So now let's see the phase part. Okay. So 10K 1 UF. I'm using the exactly same value. What are I using? I'm using 300 hertz, right? I use 300 hertz. Okay, 3 volt. Exactly the same was what we had on the scope. Okay, so now let's do this again. And what's the phase I get? I get 86.22, 86.227 degrees. Okay, so I'm hoping to get the same thing on the multisense. All right. Okay, so when you run it, you will see something like this. Or at the beginning, you will see something like this, basically. Okay, it's really messed up. It's very hard. Obviously, you can't really tell what is this, right? The important things is just like when you do it in person. Is this time-based channel A, channel B scale? Scale is your life-saving things. Okay, you have to change this. See, if I decrease it, it will be more messed up. If I increase it, hey, it's a little bit clear, but I still can't see the peak. Although the peak is not that important, but we can adjust that. So when you adjust it, you can see it. Hey, it's much better now. Isn't this much cleaner to see it? Now you have everything here. Okay, the 2 cursor is on the left. The 2 cursor is hiding here. I don't want to show you. Okay, but if you move your mouse to the left hand, you will see this pointing figure coming out. So grab it, and then goes to where the 0 crossing for the green wave. Don't worry about the circle, just stick on here. So move this to this point. Remember, there's a 2 on top. This means it's giving you the T2 points, 74,176 milliseconds from here to here. And now move your 1 to where the red zero crossing. Okay, it's giving you 841,210 milliseconds. So this is delta t. This is your delta t. So let me write this down. So we have 841.210 milliseconds for delta t, right? We need to know the total period. Okay, just like the people asked the questions before, does a if I use a red to red or green to green, doesn't matter, it doesn't matter. For the full t is the same. So now I grab this one to where also the rising part. My total t is 3.327 milliseconds. Remember, 1 millisecond is 1,000 microseconds, right? So all I have to do is, so the calculation is very simple. It's just this one here. Okay. Okay, the thing is 841.210 US. That's 337 US. Okay, let me see what is that number. 841.21 divided by 2, sorry. 3327 times 360 is 91 degrees. It's very close to what I have on the scope, which remember we get is 86.227. Those are fine in the range. I mean, it's not really huge difference. As you can see, it's close to 90 degrees. Okay, so that's basically any questions? Let me show once again. I'll select 2 different cursor in the keyset. Okay, yes, no problem. Okay, so now let's go to the video part. Okay, video part. Okay, so as you guys can see it. All right, so the key is this button, cursor key. So when you start it, press the cursors. Okay, it will have a mode. The first thing is the default mode on the cursor will be manual mode. Okay, you press this, and then you see the entry here. Choose track. Okay, and then you can choose which source. So the 1 means channel 1, 2 means channel 2. One as you can see it is in the green one, right? Because it's already labeled green. The channel 2 is labeled, sorry, channel 1 labeled yellow, channel 2 labeled green. So saying I grab the channel 1, okay. So you move it to where the zero crossing, okay. You move it to zero crossing, simple and easy. Right now, I'm going to switch to another cursor because you need 2 cursors in order to find a difference. But my cursor 2 is on the source 1, so I'm going to change to source 2, which is going to be the green one. As you can see, I'm moving it. Okay. Now let's move to the zero crossings. And we got that point. We got 800 US, a little bit different than what we have on the multisun. We have 841, but not a very big deal. 800s, okay. Because remember, there is a tolerance on our actual resistors as well as the capacitance, everything's noisy from the real world. So the value will be close, but won't be exactly the same. Right? Okay, now the next thing is you move this to where the actually this need to be 1 to the other zero crossing point. This is your total period, 3340 ms, which is exactly the same thing we have as before. Then using the delta t divided by total period times 360. Because why we're doing that is because from this point to this point, see, from okay, so from this point, you see the yellow wave to this point is 360 degrees. We try to find how much is this. So we basically using ratio, saying here to here is 360 and the time is 3340 ms. Then if we know that, then if we go to this one, sorry, okay, if we go to here, If we know that, then we also can tell if here to here is 800 µs. Use a ratio relationship, then you can know the phase directly. There is a direct way to get the phase measurement on the scope, but we don't want to use that yet, okay? We'll show you that later on for year 2. But for year 1, just learn this way because it's very important. A lot of measurement, you need to understand it from here. All right, any questions? Okay, I guess it's good for everyone. Thank you for coming. Any other questions? No? Good. Okay, any questions you can also ask me on the discussion board on the D2L. All right, it should be very simple, but you got to spend the time because it's not only for this course, all the course afterwards. Many courses you're using scope a lot. All right. I hope you enjoy your weekend. Okay, take care. Bye bye.